I want to thank John Lizzie for the presentation he just gave us here. We have another excellent keynote presenter this morning. We have George Whitesides from Harvard University, and also the Whitesides Research Institute, and also involved with soft robotics, which I'm sure he's going to mention. He joined Harvard University in 1982 and was department chairman for a number of years there. He's the Mallinckrodt Professor of Chemistry from 1982 to 2004, and now he is the Woodford and Ann Flowers University Professor. He's here to speak with us this morning on a very exciting field in the robotics sector at this particular time, particularly with respect to grasping and sub-movement and other types of things on soft robotics and soft devices. So with that, I'd like to welcome George up to the stage.
Okay, audio is clear. You guys can hear from the back? Yep, okay. So the last day has been fantastically interesting for me, as is any meeting in which everyone that you meet knows more about what you're talking about than you do. It really helps. So I've learned a lot, and some of it's very interesting, and some of it's actually a little surprising. What can someone like me, who is I work with postdocs mostly in the university, bring to an audience of this sophistication? The answer is I'm clearly not going to be able to tell you how to do your business better than you do it. That's out of the question. And in fact, I think that any idea that what goes on in a university can really compete with the sophisticated engineering and the cost of capital and the availability of background that you find in a big industry like GE, it just can't be done. So what we can do in principle is to bring some new ideas. And so what I'm going to tell you about is an idea or class of ideas which is not represented, at least by most of what you've heard. And this has to do with materials that are soft, with a lot of biomimetic stimulus, with the idea that nature has ways of teaching us about how to accomplish tasks and movement and sensing and things of that sort, which are not perfectly obvious when you start from something that's a mechanical device, and which will, in fact, I think, solve some problems. So what I'm going to do is to give you a little bit of background as to why I think this area is interesting, and then a bunch of examples at the university level, and then a concluding section, which is pure speculation on areas where I think that there might be something new here. And I should say that I think that the basic approach to thinking of something that might be commercial and useful is to say, is someone here doing it? And if the answer is yes, then the answer is we go look elsewhere, because there's just no chance of getting into that. So what do I want to talk about? Who cares about soft robots? One of the things that you'll find me doing is this periodically. I just had both lenses replaced, cataract surgery, and it's wonderful, except I have no depth perception. So why soft robotics and actuators? And most of what I'm going to talk about is actuators, because we have some things that move around, and I'll show you something about what they are. But mostly it's about the other things. What to do with them, and then an important point, and this is one of the points that might be interesting, which is what does material science have to offer? Because I think there's some new ideas here. So let me start with a stimulus. And when you say what's new in robotics, what's new, one thing that could be new is the ability to do this. And the point in this is that this is, after all, a very sophisticated device evolved by evolution, which can do things that we simply cannot do. And it uses a series of structures that we simply do not use. For example, this organism, every tentacle basically has its own brain, what I'll call as a brain. But it operates on the basis of things called hydrostats, which are a hydraulic structure very common in biology, also your tongue, your penis, if you have one, things of that sort, but not used in anything much else. So we started with the idea that an octopus has an enormous amount to teach, and where can one go? And the project that we started with, I show because it's interesting in terms of the objective. This was a DARPA project, and the idea was, can you build something that looks like a Coca-Cola can that will unfold, walk across the floor, find a crack under a door, crawl under it, and then reconstruct itself into a Coke can on the other side. And the answer to that is that we have not put all the pieces together, but interestingly, essentially every piece of that has been done in a demonstration. So you can do interesting stuff. And I want to touch on one other issue, and that is the issue of work and replacement of work by robotics. This is less important in areas like complex inspection, but more important in many other kinds of issues. And the example that I like to use is this one. And that is that there was an initial revolution in robotics of a sort in the mid-30s. And this was the invention of washing machines and dishwashers. And what that made it possible to do is to take 50% of the population of the United States, otherwise known as women, and release them from these really pretty boring tasks to go do things like being doctors and telephone operators and teachers and CEOs and whatever they've become in the modern world. But the point was not that it replaced jobs. It did, in fact, replace jobs, the machinery, but it freed smart people to go do more interesting things. So that when you think about that, and then you think about the very large numbers of people who are hired into a e-commerce warehouse at Christmas to do the work that gets done there, it's not great work. And so we'd like to find ways, one thing we would like to do collectively is to find ways of freeing those people to find more interesting things to do. And one of the interesting questions is going to be, what is that more interesting work? So I'm not too concerned with the idea of replacing jobs. What I am concerned with is replacing jobs with what? And that requires creativity for the society. All right, so why soft actuators and so on? There are a bunch of reasons here, which I can see if I look closely. It's calibration, when we ask the people. An important issue which we've paid attention to is simplification. And why simplification? And the idea there is that if you have a new technology and it's complicated at its outset, it's hard to make it work. If you have a new technology and it's really, really, really simple, then people can start building things with it and trying it. And what we work with are pneumatically actuated elastomeric structures, which can do interesting and useful things, but they're really simple. Low cost, yes. A very interesting idea to us has been something that's proved to be useful, which is what we call the material as controller. Because with the systems that most of you all work with, you have hard structures, you have joints and things of that kind, and they are linear in their behavior, designed to be so, and they operate with pretty conventional linear control loops, and it works fine. With soft systems, the characteristics are that they're almost all nonlinear. They do motions which would be exceedingly difficult to do if you were trying to do them in hard structures. And they're really simple. So it's a different idea. Because they're adaptable, what that means is that the material will enable you to do things like grasping that would be quite hard to do if you were doing it using normal mechanical methods. And there's a lot of interest in that. So what's the stimulus? The stimulus is going to be biomimetic, a big deal with simplicity. An issue, yes, let me bring this up. One thing I would love from you all is opinions. And there are two opinions here, or two issues which are really pretty controversial when we talk to people. One of them is, how important is it to build systems that are completely untethered? And if you think about inspection, it has to be untethered. On the other hand, if you think about an assembly line, it doesn't make any difference. You use it tethered. How important is that? We can do both, but we tend to work with tethered systems simply because they're easier to work with right now. The second issue is, what do you think about the issue of pneumatic or hydraulic versus electrical? Because in much of what we think about, we use pneumatic because it's safe, it's simple, it gets around a lot of problems, and allows this business of adaptability. Electric can be done, but it's more complicated. So opinions would be welcome for this. Now, I'm not in the business of shilling for books, but this is one which, if you haven't read, is really worthwhile reading. It's by John Garnier, and it's a history of Bell Labs. And most histories of Bell Labs say brilliant physicists, unencumbered by practical financial constraints, invented solid-state physics, collected Nobel Prizes, made the transistor, and changed the world. And the fact of the matter is that according to the research director there, that isn't really what happened. What really happened was that everybody who was hired to solve a particular problem, which was making a more profitable telephone system. So I'm happy with that, and I think we would all agree with that. But he makes the following interesting point, and that is that he breaks up the process of broadly innovation into a piece which is science, which he says is fairly easy to get anywhere, invention, by which he means some kind of prototype device, which is a little bit more difficult to do, but it's doable. There's a piece which is development, which is the hard part of doing the engineering, finding out about registration, dealing with shelf life, dealing with lifetime in operation, all the rest of that kind of thing. And at the end of that, you have a market. But his point was that until you have a market, you have nothing. The net value of everything else is zero. So one of the questions is, for a new technology, how do you get most rapidly to market? Which leads me back to simplicity, which means it's easy to do. So, I mean, to me, a lot of a new business depends on that. And let me show you a model which I'm going to come back to, but it provides a sort of starting point. That's a bicept. It's not a particularly impressive bicept, but it serves to illustrate the point. And the question is, can you imitate this? And this has been one of the classic problems in soft robotics for a long time. And I want to show you how to do it, which is this way. That's a linear actuator that does that using PDMS, polydimethylsiloxane, as a elastomer. But the operation of it is very much like a muscle, but the mechanism by which it works requires taking advantage of a series of nonlinearities in buckling. So the whole structure is based on buckling structures, and I'll show you why that is so interesting and to us important. All right, this is a point which has to do with simplicity. The first paper in this broad area was in 2011, which shows a gripper swooping down, picking up a raw egg. Why is this interesting? It's interesting for the following reason, that lots of robots can pick up raw eggs, but they have to have sensors on the end so they don't crush the shell. They have to pay attention to what they're doing. There's a computer system that controls all this. It's not straightforward. Here you have a pneumatic actuator that's applying about 7 pounds over atmospheric. It cannot apply more than 7 pounds per square inch to the surface of the egg. So the entire structure is self-regulated in the way it interacts with the surface that it's making by the nature of the materials in the structure, which dramatically simplifies the task of making something work. And as a result of that, it was able, those of you who heard Mark Ciapinelli talk yesterday, to go to this structure, which is now a company which is, a perfectly fine small company. It's, somebody mentioned that it's just done a financing, and it's doing fine. But if you look at the products, they're essentially the same thing as this. Much better engineered, much more sophisticatedly done, and attached to solve a problem at the end of commercial commodity arms and things of this kind. But simplicity made it possible to move pretty rapidly with that. So how does this work? The basic idea is probably familiar to all of you, but it's interesting to compare in terms of manufacturing. You make a mold, normally using 3D printing for what we want, and we make structures that are sort of this size to this size. It's that kind of size range. And you then pour an elastomer in it and you cure it. And this is not the only way of doing it. It builds a channel system into the system. You put it together with another piece, and when you inflate this, what happens if you have anisotropic structures? This part that is difficult to stretch, the one in which the tensile modulus is high, doesn't, and the one which is more elastic does, and you get net motion of the structure. One of the interesting parts about this is that it involves heavily a class of materials which is both completely explored and completely unexplored. The completely explored part is composites, because everything that you've talked about is basically a composite in some way. But the idea of composites of soft structures, of elastomers, is almost completely unexplored. Nobody works with them. And that means that all of the anisotropies in materials, the joint properties that you can bring by putting together two two or more materials in different ways is all open here to be exploited, which means that this material as actuator or material as something else is completely unexplored. And from the point of view of a new technology, this is a good idea for the reason that it brings something new to the story. Now let me show you how this works. There it is. It reaches down, grabs the thing. We're just exerting pressure and pulls it up. That's all straightforward. And what you see, the thing going up is just a string, and the thing going down is the pneumatic source. But let me show you a little bit more about this, because it's not as obvious as it seems. If you look at the structure in the upper right-hand side, well, let's look at the lower right-hand side. What you see is a series of chambers. Look at the upper left-hand side, and you'll notice if you look carefully that under constant pressure inflation, the structure bends from the tip in. And that bending from the tip in is the result of something called snap-through, which is another nonlinearity of unusual materials. So it's something which you can exploit this way. Now you go from here to this, which Mark showed you some of. You can make these things to build, to pick up heavy loads. They pick up, if I can make it work this way, they'll pick up things. The same device will pick up something that is very easily crushed. This is what's turned out to be one of the major applications of this at the beginning, which is food handling. Because trying to find mechanical pinchers that take soft things like that's the thing we all do every morning, and which is to deal with that kind of problem. But at the end, there is one structure I want to see at the end. I mean, this just shows, I don't know where it is. It's not worth worrying about. So where has that gone? And where it's gone is what you see here. Let me go back. Let me find how to turn this. Here we are. Now this is an example of one of the commercial products, which is, the thing that's interesting about it is that everything in this is, as it were, off the shelf. That is the arm, the vision system. But the vision system can be easy. The arm is well adapted. But this is real time. It's picking and placing. And the thing which is interesting about it is primarily that because the grippers are adaptive, you don't have to worry about where you put the gripper or controlling the gripper other than approximately. They'll pick up, the same thing will pick up equally well cauliflower or something else, or irregular soft structures that damage. And that's a useful skill. Another thing which is interesting is this, which is that what you see there is a hand made this way, and it folds up. And the point now is to make the case that we really are hammering on things. But it, if you then inflate it, it does what it's supposed to do as a hand. And you don't see it here, but it has knuckle-like structures just by changing the width of the channels. One of the things that's interesting about these is that they're so light that you can throw them off any building, and the terminal velocity they reach won't do them any damage. They're fairly easily cut, but they're essentially indestructible by pressure. It's the opposite with hard structures. Hard structures are quite resistant to pressure, but cutting doesn't get them anywhere. Anyway, if I took that structure and I pound on a small robot metallic of the same size, I do a lot of damage, but I can't cut it. This one I can cut, but I can't damage by pressure. So there are new things there. All right, that's sort of the past. Let me show you a couple of ideas. And this is centered around the basic notions of buckling, where there's an interesting idea, negative pressure and nonlinearities. So if you look at the upper left hand, what you see is a car post-collision. And all of you are more than familiar with the idea that as you take stiff structural beams and you cause them to buckle, they do, but the process is irreversible. If you take the thing down at the bottom, which is another beam, it's an elastomeric beam, and you put pressure on that, it buckles at much lower pressure, but it's completely reversible. So what happens is that for soft structures, buckling becomes a mechanism of actuation. For hard structures, buckling is a mechanism of failure. And that difference is one that opens a whole door of possibilities and things that you can work with. And I'll show you a little bit of solid state physics because it's fun to see how this works. What you see here is work done originally by Katia Bertoldi. And if you look carefully, what it is a series of holes in a PDMS slab. So it's actually a PDMS air composite. And you squeeze it from the sides, and as you do so, you see a phase transition. So it goes from a cubic array to a C2 array, in which the holes have changed from round to triangular. And you say, well, who cares about that? And the answer is you go down to this structure, in which the holes have been ellipsomeric. And as this structure actuates, what happens is it actually does what you see on the top, which is it does a rotary motion as opposed to a just collapsing motion. So what you've done is to take a single actuation, which is this kind of structure, and convert it into something that does something fairly complicated, because you're seeing two separate areas where this process can be described as converting just this into this, more properly this. And this ability enables you to do something which we all want to do every day, which is this. And it's a single input, which is negative pressure in this case, which enables you to get two things moving this way, counterclockwise motion. Very simple. We haven't done anything, but it would be much more complicated to do it other ways. And by the way, one of the things that works in this is that in order to get all of these with exactly the same pressure on them, what you do is put a thin elastic membrane over the entire thing, and then you evacuate it. And when you evacuate it, atmospheric pressure does all the work for you. So it provides another mechanism for doing something that doesn't provide, in this case, great force, but it gets things done. So now to look at how the mechanical actuator that replicates the bicep works, what you have to do, and it's not worth the effort to spend a lot of time doing it, is to look at the structure, which is one of these things that you see in Cutaway. And you can think about that as a series of beams that are elastomeric beams this way, braced by stiffer elastomeric beams that are this way. And when the system compresses, what happens is you get reversible buckling of these beams, and that provides all of the motion. So it seems very simple, but it's actually not. That is to say, it's not in terms of its concept. It provides linear actuation, which is very lifelike, which basically cannot hurt you. It is fully collaborative. It can be made to be pretty high force, but more properly, what it enables you to do is that, which is a stupid arm trick. And I want you to know that it only took 4 tries. So we get it to work 1 time out of 4. All right, efficiencies. One of the things we don't know with these systems, and actually as far as I can see, you all don't know with many of your systems, is real thermodynamics efficiencies. I'm a chemist by background. I love statistical mechanics, and I love thermodynamics. And the question is, how do we actually put together some program of investigation that tells me whether a coal-fired plant producing electricity, shipping it to somewhere and running an electric motor is actually better than something in which you take the electricity, run a compressor, and compress air, and that does whatever's going on? I don't know. If you look at PDV work in these systems, from the gas input to the work that's done, it's about 35% efficient. So it's not bad. That's about the same thing that you get for an automobile engine, but it's a different calculation. Now, let me show you a little bit more about this idea of buckling. What you see there is a polymethyl methacrylate sheet, or polyvinyl acetate sheet, I forget which, that simply has a bunch of circles so that you can follow what goes on. And in the back is a little pocket which we can inflate. And when you inflate it, it applies pressure in the center, but because this system can bend this way, but it cannot compress this way, it distorts. And the distortion looks like this. And an interesting thing about these systems is that you can program the material to do that motion by just bending it once. You bend it once, and it will do that again, and you will do it wherever you bend it. So you can, set this up, and although the systems that we have are That particular system is probably only good for a few hundred cycles. If you work with a elastomer carbon fiber sheet, those will, as far as I can see, run forever. So it's possible, it's actually a point that's worthwhile making. Many of these structures that we make, some of them have been tested for cycle time, and numbers of tens of millions of cycles are not unreasonable numbers. So they actually provide, again, something different. If you have a bearing that's doing that, grit gets in it, you have to clean it, you have to lubricate it. If you have something that's just doing a single piece of material doing that, the only thing that happens to it is if you stress it too far, you begin to get bond breakage and auto-oxidation. But basically, elastomers are unbelievably durable if you treat them in the right way. So now this leads us into something that we're quite interested in, which is what we call life that never was. And if you look at the evolution of motion, we like the idea of working with snails and things like this that provide solutions to problems of grasping and eating and searching and getting out of the way, but they're pretty sophisticated. The question is, if you look at that world and you say, what happens if you go back in time to the point where life first emerged? There must have been other ways of doing it. And the idea is we can, with this kind of thing, test it. And what you find there is a walker. And the walker actually works pretty well. And it's just based on this buckling thing. There are two separate questions with this. One is, why didn't this emerge in evolution? And that's a question that we in university should deal with. But the second is, could you use that kind of motion to provide a walking platform for other things with different material sets? And I don't know the answer to that. And it's not going to be the kind of thing that you all use mostly, but if you're thinking about something in which you want to use the structure once and it gets thrown away, for example, inspecting for mines, why do we take $25,000 or $50,000 worth of treads and things of that sort, send it into a tunnel, have the bomb blow up, and then you're out of money, when you can send something that will probably work pretty well for about $1 and see what's there? It opens a different structure to the way you can think about what's doable and what's not doable. Now let me show you one other example, which is speculation. This structure is one of my favorites. I like spiders, some spiders, many spiders I like. They don't like me, but spiders. And the question is, if you look at this kind of thing, is there something that it can teach you about how to move around? And the thing about spiders are interesting because they're very sophisticated animals, but they have pretty unsophisticated legs. And don't ask me why that came out of wherever. But the way in which a spider's leg works is this. You have a tube that's rigid. You have another tube that's rigid. You have a very simple mechanical hinge. And then you have something in between that basically blows up. So and then there's a hinge that brings them together. So if you've ever looked carefully at dead spiders, they're always with their legs like this. And the reason for that is that the relaxed state of a spider's leg is curled in, and it's expanded this way. So the question is, can we do this? And we do this, let's say, using an unsophisticated procedure, which is to use tubes which are basically polypropylene drinking straws, which are beautifully fabricated, absolutely uniform, and cost nothing. And then inside that, we put a combination of a small bladder and an elastomer. And what do you get out of it? And what you get out of it is this, which is something that's using a spider type leg, but it is 6 of them rather than 8 as it is in a spider. Now you say, this is completely useless, isn't it? Well, exactly the same thing can be done with light titanium tubing and with better elastomers. And I think we could build these, we haven't, but I think we could build them 6 feet across, actually carrying pretty substantial loads. So I think if you look throughout biology, you find everywhere structures that we don't know how to use that are based on combinations of either materials like chitin that are easy to work with, but just have never been used in material science, and then design principles like this one, which we just don't use. Have we looked at them and discarded them? The answer is no, we just haven't used them. All right, Let me show you one last system, which is sort of interesting, and then I'll finish with ideas. This is another crimping experiment. And if you take the structure on your left-hand side, and you make it a hollow tube, you blow gas through it. If you push down on it, it crimps, and then you can't get gas through it. So it's a very simple and very effective valve. And what do you do with that? And you do this kind of thing, which is you make a little cylinder that has a bistable structure in it, which it's like children's pop-up clickers. It can be either up or it can be down. I can't get my fingers to work that way, but it can be either way, and it's metastable. So if it's up, it's up. If it's down, it's down. And we arrange these things in such a fashion that when it's up, it crimps one gas stream. When it's down, it crimps another gas stream. And you say, well, why is that interesting? And I'll just show you a simple demonstration of its doing something. And what it's doing here is acting as an off-on valve. Yeah, here we are. To pass gas autonomously from one line to another line. It does that, and if you look at the volumes and the sizes, we work with robots that are this size, so we want a fair volume of gas. I don't want this to be a micron-sized thing. Well, why is that interesting? And that is that if you go down to the lower right-hand side, what you see is that this structure is putting together the Boolean, not gate kind of structure. And you can, for example, make ring oscillators with this. So you see a structure for a 3-stage ring oscillator up on the top, and you see this thing working. The same kind of thing allows you to make all of the Boolean operations so that we can do full Boolean algebra with this. And at the same time, you can do things that transistors can't do because it's a little bit more flexible. Is this useful? I don't know, but it offers the opportunity to do onboard processing in a way that you can drive a car over, and it doesn't make any difference. All right, then one last thing. You can, of course, put in all kinds of interesting structures for sensing and whatever, and this is some work done by friends who do this, Katie Bertoldi and Rob Wood, who do this mostly to show it can be done. It's possible you can get good haptic sensors this way, and they may be useful for more complicated structures, but they do have the problem that they're more complex to make. So it's done by 3D printing. All right, that's enough for new stuff. Let's talk about briefly what's next. The work that we've done has mostly been done with elastomers that have approximately the mechanical properties of a rubber band. I mean, it's not quite the same thing, but it's that kind of thing. So we are making structures now for biomedical applications that look like Jell-O. And it's easy to do. The more interesting one to me is this thing in the center. If you think about structures that are materials that you can form in interesting ways that are really, really tough, it's hard to find something better than a heavy-duty truck tire. So there's an entire class of these structures that will use higher pressure actuation in one or another, which have the characteristic that they will be completely different from anything that exists. No biomodels for that kind of thing. And one of the things I've told my students I would like them to do is to build me a structure that will tear a car in half. And so far they seem unenthusiastic about that, but I think it's a perfectly good idea. And it would catch attention. What are some opportunities? E-commerce. I mean, one of the things that I learned from the last day was that I'm going to remove this from the list because it's just the cycle lifetime, I think, for a new idea is going to be so short that people who get involved in it are really very brave and have to be well down the road to get anywhere with it. Agriculture, no doubt about that, because things that are soft, where you want to work with materials that have the characteristic that they're non-bruising, non-damaging, unannoyed by pesticides. They don't care whether it's raining or not. It seems like a plausible thing. Food, we talked about. Consumer products, this idea of heavy industrial is an idea that stems with the truck tire. But if you think about jobs that you would like to remove people from, it is mining, dealing with high radiation environments, things of that sort. Moreover, you don't want to recover your devices there. So that in Fukushima, you want to send in the system, you want it to be completely radiation insensitive, and you want to cut the cord when it's once it's in. So I think there are actually quite a range of those. Biomedicine. You look, as one of the speakers yesterday said, for inevitabilities. And one of them is not the high end of biomedicine, as in the Da Vinci surgical device, but the low end, aids for nurses. And if you go to any hospital management structure and you talk to the nurses, everywhere you look, they have problems that are just almost impossible, which they have to solve every time. So a patient comes out of surgery, they start going into spasms of one or another sort, and they weigh 300 pounds. What do? And you need a non-bruising way of picking them up, rolling them over, doing pretty straightforward things, but you have to do it in a way that metal fingers won't do it. So doing it softly is actually a big deal, and there are just an infinity of those, and I'll show you just one example there to give you an idea. And then hazardous jobs is obvious. But here's an example of something which, again, has the characteristic that it's really simple. So if you have a stroke, it is extremely important, if your hand isn't working, let's say, to start flexing it essentially immediately, as soon as you can do it, even if you require mechanical aid, because otherwise things happen that make the damage irreversible. So you buy a glove from Sears and Roebuck, or whoever happens to be doing it, and you put on each of the fingers, you put one of these flexors. It costs nothing, and it works really well. And so that will sit there and do this kind of thing at great length. But one of the things that Connor has done is shown in the upper left-hand picture, where you see I think a veteran in this case, who's had damage to his right arm, the structure on whichever side it is, so that arm doesn't have the strength to pick up something. It can get to the right place, but there's very little motor strength left. And so you build one of these gloves, and you build in a slightly complicated device which senses actuation of the muscles in the arm, and what happens is this. So he can reach down and pick this up, and then obviously with some effort, but it's a lot better than nothing, pick it up and turn it. And again, this is the kind of thing that by the time you get finished with it, it's actually very cheap. And that means it can be used by a large number of people, including the elderly in the society who are beginning to fail in their various functions, such as me. So I'm completely for it. Other things, for this audience, I think I'll skip through this a little bit, because this is what can be done with soft materials generally. And the list of things that are involved here is very large, but it is an area of material science which has simply not been explored in connection with this kind of thing. So it's all open to work on. And then more of the same kind of thing. And sensors and controls. This is one last thing where I want to ask a opinion, and that is, there are people who say, look, it may be simple, it may be soft, but you still have to have embedded sensors and controls. You just have to have that. And I say, why? If I can pick up apples without any sensors and controls, why do I need to have sensors and controls? For whom? And it's an intractable kind of argument to have, because if you believe in sensors and controls, you believe in sensors and controls. What are the boundaries to adaptability and autonomy in this particular connection? And then to get back to it, can the material be the controller? And can it also be a sensor? And the answer is it can be both. You just have to think about how to do it. These are the people who did it, and that's, since you don't know them, it's a nice list, and they're very nice people, and some of them are extremely smart. Thank you very much for teaching me so much in the last day. It's been a real pleasure.
Well, we have time for a couple of questions. So does anyone have a question for Dr. Whiteside?
I have one.
Yep.
The example you showed with I guess I call it the spider walking.
Yes.
You mentioned that the material can replace the controls, but how do you control the walking just through the materials?
Well, there are two approaches. I mean, if you look at that, the way an ant walks, it has 6 legs and 3 are always on the ground, so it maintains 3 points. So if you want to turn, there are sophisticated ways, but the simple way of turning is just to, send 2 pulses on the left-hand side and it'll turn. So it depends upon what you want. You can make it really simple. You could, in principle, put each leg under separate control, at that point you begin to think of more complicated issues. But you say, is it necessary? And if you think about, for example, search and rescue, which is something that I'm interested in, with search and rescue, if you have treads and you have rubble, treads don't work all that well on rubble because the rubble tends to crumble and go with the treads, and so it's on a sliding bed. And if you look at the kinds of things that are everywhere in a scene of devastation, it's always the insects who are getting along just fine. And so, the idea of having legs means you can pick up a foot and put it over something or adjust it when it goes down to something. And I don't know how it's going to work out, but I think that we shouldn't neglect legs as being a method of getting around.
So you mentioned that your interest is in search and rescue.
Yeah.
I was wondering, do you imagine that these kind of search and rescue robots, would they be all tethered, or have you explored untethered
We can make
possibilities?
untethered systems, but we have done much more with sort of gripping and just sort of getting basic motions down. But the kind of thing that I think is particularly interesting is, this is not impossible, that we find that customers coming out of a subway are foaming at the mouth and dying because that's chemical terrorism. And you say, well, what's going on? The instinct of the people who are searching, or who are the first responders, is always to go into the scene. I mean, they're brave people and they know what they're doing, and they go into the scene where they become part of the problem. So what you'd really like is something that will do a simple task, which is walking down the stairs, sense what's there. And sensing what's there can be done actually very straightforward chemically by transferring mass. We've done a lot of this stuff. And you can send out a sensing liquid and then pull it back. You can do all kinds of things. And if, after a while it's wallowed around and whatever's there, you don't think this is going to be very attractive to deal with, you cut it. So I think the answer is that there will be tasks that are based on the basic idea of disposability of the device, as opposed to the elaborate control and recoverability of the device, which is a different structure altogether in thinking about what you do. But I think a lot of search and rescue is better done if you have a one-time use system and you just toss it when you're done.
Question here.
Thank you. That was a great presentation. My question had to do with dealing with a compressible, with air as an actuator,
Yep.
and the speed limits that you may have because of the compressibility. Have
Yep.
you done any studies to see where your limitation is going to be?
Yeah, the issues there are very straightforward because the reason we use air is that it's here and we can vent it into here and there are no environmental problems of any sort. It has the disadvantage, there's the PDV work in compressing it, but on the other hand, you have to put in the work somehow if you're going to get work out. So whether you put it in electrical potential or in terms of pressure is, in a sense, neither here nor there. But the velocity in which you can move air from place to place depends entirely on wall shear, basically. So if you have a little tube, it doesn't move all that rapidly, and you have a big tube, it moves more rapidly, but if you have a big tube, then you have to drag the weight around if you're going to move it or whatever. None of that is important if you have a stationary object, because you just set up the tubes to do it. But if you have something which is a autonomous object, then big tubes and throwing away a lot of air is a problem. So I think you're quite right in that. You get away with it, of course, as I think we talked about briefly, by doing hydraulics. But the problem with hydraulics is that fluids are heavy. So that if you're moving stuff around, air is much simpler, it makes for lighter, cheaper structures. So there'll probably be some kind of trade-off between different kinds of applications. Hydrostats, which are enormously flexible structures, are all fluid, so far as I know.
We should probably wrap it up. I have just one question. You talk about pneumatic and hydraulic control. Are there deformable materials that can be actuated using an electrical charge?
Yeah, and the answer to that is yes. There are a whole bunch of them. The ones that are most popular now are something called dielectric elastomers. And the idea in that is that you take 2 electrodes and you put them on top of a deformable structure. And so you apply a voltage across them, they squeeze, and as they squeeze, they change that dimension, but they also shove stuff out the side, and people are exploiting both of those. The trouble is, it takes 1 or 2 kilovolts to get significant motion that way. And that, I think, doesn't bother you for many applications, but if I'm going to have somebody inside me doing something, I don't want them doing with 1 or 2 kilovolts. I prefer half an atmosphere.
So with that, we're going to have to wrap it up. We are out of time. I'd like to thank George Whitesides for coming here today and presenting. Very interesting.
Thank you.